Okay. So we left off talking about the binomial distribution. Let's go. Oops, that was mine. All right, so we had this equation, all right? And we kind of worked through a couple examples. And I think the one we left off on was this one where we had, well, actually, the last one maybe we worked through was this coin flip one, and then I showed you some other things about how, you know, we write these factorials 10 factorial, so that's 10 times 9 times 8 times 7, all the way down to 1. But then a lot of times if they get too large, there's usually things we can cancel to make the work a little bit more easy. Okay? So last class was more about kind of the procedure of using this formula. Now I want to see how we can kind of push it a little bit further. So let's say we have this example where we had exactly 5 kind of adults selected, and we were asking each adult if they had a college degree. And we know from some data that the probability any one person in the US, the probability that any one adult has a 4-year college degree is 30%, or a probability of 0.3. Then let's say we want to find the probability that exactly 3 people out of those 5 have a college degree. So my n here, I'm asking 5 people, right? So I'm running this experiment 5 times. The probability that I'm interested in the number of successes is that exactly 3 of them have a degree. And the probability any one of them has a degree is 0.3, right? So I'm looking for the probability x is equal to 3. I've identified my number of trials, my probability of success. At this point, it's just a matter of getting everything plugged in, right? Plug in n is 5, x is 3, and then p is 0.3. Okay? So this is kind of where we left off, kind of thinking about how we just get these plugged into the formula. I said start to kind of work through some of these, make sure you're kind of comfortable. You know, find that factorial button on your calculator. If we have large numbers, think about how we could cancel things to simplify. And we'll review a couple things that we talked about last class as well, but I want to introduce some new concepts. Okay? So let's say I calculate this probability that x is equal to 3 and it's 0.13. Right? So if I ask 5 people, there's a 13% chance that exactly 3 of those 5 have a degree. What if, maybe it's a little bit easier to think about it this way. Let's say let's do a different example and I'll kind of come back to this. So let's say I flip a coin 10 times. Okay? We know the probability that I see a heads on any one flip is 0.5. On average, if I flip a coin 10 times, what do you think the average number of heads I usually get out of those 10 coin flips is? 5, right? It's kind of intuitive, but what you really did there, and we'll skip ahead and then I'll come back, is you took the number of trials, 10 coin flips, times the probability of success on any one coin flip, 0.5, and you multiplied those together. Maybe that's not what you thought you were doing, but like this formula is fairly intuitive to find the mean for these binomial distribution examples. So when you said that 5 was kind of the average or the most likely outcome you would see, we're really finding the mean there. Okay? So the mean is going to be kind of our most likely outcome, right? It gets a little bit weird when we come back to an example like this because, oops, let's say I want to find the mean from this example where it's the same setup. So I've got 5 adults, right, 5 trials. The probability of success is 0.3. So the average here would be 5 times 0.3 or 1.5. Well, this is a discrete random variable, right? I can't see exactly 1.5 as the outcome. I could see 1 out of the 5. I could see 2 out of the 5. So anytime we have a non-integer mean, the integers nearest to it are the 2 most likely outcomes. Okay? So let's go here. I'm going to draw something for you before we kind of go to this next problem. Sometime today. There we go. So if this is a little dark, I couldn't find the remote today to kind of increase the brightness. So hopefully someone didn't steal that. But let me know if you have any questions. So what we're doing here is we're looking at 5 people. So 0 could have a degree, 1 could have a degree, 2, 3, 4, or 5. If we think about this y-axis as representing the probabilities of these different outcomes, right? We said the mean was 1.5, which means that 1 and 2 are the most likely outcomes, right? Of the 5, they're the most likely outcomes, okay? Now, I think it makes sense in the coin flip example, and then we'll come back here. If I flip a coin 10 times, the average is 5. Well, so I found the probability that of 5, it should be the highest. Well, then what's the probability I see 6 out of the 10? Well, that's a little bit lower. Well, what's the probability I see 7 out of the 10? It's a little bit less likely. What's the probability I see 10 out of 10? Well, that's a lot more unlikely, right? What about the probability I get 0 out of the 10? Well, that's also very unlikely. So the idea there is, as I move away from this mean, really in either direction, the probabilities of seeing these number of successes should be decreasing, right? It becomes less and less likely I see outcomes further from that mean value, okay? Any questions on that? It should be, this is going to be kind of an important principle that will help us navigate a lot of these questions. So I just found, not drawing this very well, but, or at least straight, I shouldn't say well, but just straight. We found the probability x is equal to 3 was about 0.13. So what do I know has to be true about the probability x is equal to 4? It's going to have to be less than that, yeah. So if I wanted to, I could plug everything in. My n is still 5. My probability of success is still 0.3. Now my number of successes I'm interested in is 4. I could plug that into the equation and get that. But if I were to ask you a question, let me see. I think let me see if this will work in class. Nope. I had a feeling I might have to hit that. I'll show that to you. I'll leave this up here again. But okay, so in case you were still writing some of this down. So once again, when I switch back to these slides, what I've left up is what I was drawing. So these on Zoom, you can kind of hopefully see this. So if I think about it has to be less than 0.13, the only answer here that makes any sense is actually A. Right? I can actually rule out every other answer. So a lot of times I'll do things like this, where if you have some previous information, it might help you then on the following question to be able to rule out some of these answers. Right? Now, if I wanted to, I could actually use those values, plug them into my binomial equation, right, and end up getting kind of 0.028 here. Okay? So this is just really oh gosh, what word am I looking for? An exercise in kind of making sure you can use your calculator correctly. Okay? Once you get everything plugged in here. So the next thing that will kind of push it even a little bit further. So we've got the probability that x is equal to 3. We've got the probability that x is equal to 4 now. What if I wanted the probability x is at least 3, right? So what's the probability at least 3 out of the 5 will have a degree? Okay. So we'll write down what we're looking for. I'll try to kind of leave this up here because I think this will help us think about it. We want the probability that x is at least 3, so greater than or equal to 3. Right? Now, if we go way back to when I first introduced probabilities, I said, when we think about the probability of an event, it's essentially the probability of all the outcomes in that event, right, minus the intersections if they have any. Well, here, I can never see exactly 3 and exactly 4 people have a degree out of 5. So everything's independent here. Everything is mutually exclusive. And so another way I could write this is it's just the probability of every possible outcome that meets this criteria that's in this event. So the probability x is equal to 3 plus the probability x is equal to 4 plus the probability x is equal to 5. Well, that's where I stop because that was my number of trials, right? The most I can see is 5 out of 5 people have a degree. Now, it's a little bit of a pain because we're going to have to use that binomial equation 3 times. Well, in this example, right, we had this was 0.13, this was 0.028. So we really only have to do it one more time. Right? So if I do this one more time, right, and I plug everything, so n factorial divided by right, x factorial times n minus x factorial. The probability of success was 0.3 to the x power times 1 minus the probability of success. No, sorry. Probability of success was 0.3 to the n minus x power. Okay. So here's where I want to kind of revisit some of the things we talked about last class, right? I'm going to just start doing some of this simplification here. So 0.3 to the fifth, I can't really do anything with, but 1 minus 0.3 is 0.7. 5 minus 5 is 0. Over here, 5 factorial and 5 factorial, well, that just cancels, right? So what I'm left with is 1 over 5 minus 5 factorial, so 0 factorial. Remember last class, what did I say 0 factorial is equal to? It's kind of a weird one. Yeah, it's equal to 1, right? So 1 divided by 1 is 1 here, times 0.3 to the fifth, times what's anything to the 0 power? I also said last class this is 1, right? If you don't believe me, do it in your calculator. I had a section yesterday and I said it and someone looked puzzled and I saw him enter into his calculator like a bunch of different numbers and verifying that yes, anything to the 0 power actually is 1, okay? So here what we're really left with is just that, right? Anything times, multiplying something by 1 doesn't change anything. Also, not to go on an aside, but I was listening to a podcast and they were talking about some people say 1 and some people say 1. So I say 1. So if that bothers you, I apologize. I don't know if I say it right or if I say it wrong, but so, really here, this simplified down quite a bit. Once we plug this in, I think it's something like 0.003 or we'll see it here in a second. But now that I have that value, now it's just adding those 3 up, okay? So sure enough, if we go here, ignore this line for a second, but we said the probability x was greater than or equal to 3. Take the probability it's equal to 3 plus 4 plus the probability it's equal to 5. That's using that binomial equation 3 times, but we'd already done that twice in the previous 2 problems. So it was 0.002. Sorry, I was a little bit off there. Now it's just a matter of adding those all up, and now I'm done, right? Any questions over that? Because I'm going to push it a little bit further now. We're okay with that part of it? Make sure the chat's open. All right, no one in the chat, no one in Zoom has a question. So let's do, so I said let's skip this line for a second, right? Where did that come from, okay? So if I want the probability x is greater than or equal to 3, right? If I think about this as event A, right, I know that I can rewrite this as 1 minus its complement. We're using that complement rule, right? So if the event A is that I see greater than or equal to 3 out of the 5 people have a degree, what would a complement be? Well, just every outcome that's not in this event, so it would just be that x is less than 3. But here, it gets a little different in that, what's the very first outcome I could see that fits into a complement? So what's the very first outcome I could see that's less than 3? 2, right? So we have to remember, all these binomial examples, discrete. So the very first outcome I could see is that it's equal to 2. The next one would be that x is equal to 1. And then finally, let's not forget, I can always see x be 0, right? Now, here it didn't save me a lot of work, right? Because in the previous way we did it, where was it, right? We still had to use that binomial equation 3 times, and now I still have to use it 3 times, right? So why the hell am I showing this to you, right? Well, let's think about a different example where this saves me a ton of work, okay? So let's say I'm flipping a coin. We'll do 10 times to make it a little bit easier, right? So what's the probability out of those 10 coin flips that I see at most kind of 9? So I see 9 of the 10 coin flips come up heads, or any number of heads below that, right? So as a reminder, I'm switching examples. We're now thinking about we've got kind of capped at n is equal to 10. Well, if I try to rewrite this, that all the outcomes that fit this criteria, this is the probability x is equal to 9 plus the probability x is equal to 8, all the way down to the probability that x is equal to 0. Well, I don't want to have to use that binomial equation, not 10 different times? That's a lot of work, right? Especially if I ask you to do this on the exam, you should have a pause and think, I've only got a certain limited amount of time. Should I really be solving this problem this way? And the answer is no, right? I'm never going to give you a problem where you would have to use the binomial equation this much, right? Just for one answer. So if I think about, I'm looking for the probability of event A, I know that's the same as 1 minus its complement, right? So what would A complement be here? X is greater than 9. But what's the only outcome, if we're capped 10, that fits this criteria? Well, the equality isn't on this, right? It's not on the complement, it's on the event I was looking for. So the only outcome that's not in A would actually be x is equal to 10, right? That's the first outcome that would fit this criteria. Well, now I only have to use that binomial equation one time and I can solve this, right? So using that complement rule is going to save us a lot of work, right? Or you can think about if this got large enough, like let's say I was doing, first of all, are there any questions on that before I keep going? I almost got excited before okay. So let's say I had n as 100 and I changed this to 99. So this is like 99, 98. When x is like 98 and n is 100, remember I'm going to have like 100 factorials and really large factorials in here. This is going to be a mess. I mean, if I have enough computing power, I can do this, but this is going to be a pain, right? But if I just change to something like this, much, much easier, okay? And instead of 10 here, right, we would be doing just x is equal to 100, saving ourselves a ton of time and work, okay? All right, so that's where that was coming from. So we talked about the mean already. It's pretty intuitive. What's not as intuitive is going to be the variance, right? So we could go through a mathematical formula to show this, but it doesn't matter what binomial distribution we're looking at, what number of trials, what probability, the variance will always follow this formula, okay? So n times p times 1 minus p, right? Or the mean, right? The mean is actually kind of hiding in there, times 1 minus p. So really the variance, what this is capturing is that the more number of trials you have, the higher the variance is going to be. Just think about it this way. If I'm flipping a coin and I flip it 5 times, the number of heads I could see is only between 0 and 5. Not a lot of variation there in the outcomes. If I flip a coin 100 times, theoretically, even though there are some low probabilities of seeing some of the values, I could see anything from 0 to 100. A lot more variation, right? So that's why kind of our variance is influenced by our number of trials. Right? But really just, knowing this equation is going to give us the variance. It's pretty easy to plug in, our n and our p and get this pretty quickly. Okay? If I want the standard deviation, what's the only other thing I need to do? I'm really trying to hammer this home because it's the same in every time we calculate a variance and standard deviation. If the standard deviation is simply sigma, I just take the square root. Right? So to go from the variance to the standard deviation, I'm always just taking the square root. Okay? So if I go back to that example, I'll skip ahead. If I go back to that example real quick, let's say I've got these 5 adults. We've kind of already talked about this. The probability of success is 0.3. The mean there was n times p, or 5 times 0.3, so 1.5. Right? We already kind of talked about that earlier. But what about the variance? We just go back. N is 5, p is 0.3. So 5 times 0.3 is 1.5 times 1 minus 0.3, so times 0.7. We actually end up getting 1.05. Okay? These should be pretty easy problems. Right? If I give you one of these on the exam or something, these should be some easy points, right? Before we end class, I'll kind of show you, I do have a formula sheet for the exam, so you will have a lot of things kind of there centered for, or in a central location prior to you taking it. So if we have these equations, pretty easy to find the mean and the variance of a binomial distribution, okay? So I have these pictures here because I also want to kind of point something else out and really hammer a couple principles home. So let's start up here in the top left corner, where I had the number of trials was 5 and the probability of success was 0.1, okay? So my mean here would be what? N times P, so 0.5, 5 times 0.1 is 0.5. So sometimes I said we don't have an integer value, like in the previous one we had 1.5, so it meant 1 and 2 were the most likely outcomes. Well, here with a mean of 0.5, it means 0 and 1 are the two most likely outcomes out of all the possible number of successes we could see. So notice they don't have the same probability of occurring, but they have the two highest probabilities, right? They're the two most likely outcomes we could see. And then as I move away from that mean of 0.5, the probability of seeing a higher number of successes starts to decline. Right? Think about if I had a really high probability of a success, so 0.9. 5 times 0.9 is 4.5. So 4 and 5 are the two most likely outcomes out of these different numbers of successes. As I move away from that mean of 4.5, the probability of seeing those lower number of successes starts to decline, right? Or it's decreasing. What if I have a probability of 0.5? 5 times 0.5 is 2.5, so 2 and 3 are the two most likely outcomes out of all the different numbers of successes. As I move in either direction away from that mean of 2.5, notice the probabilities fall moving in either direction. Okay? So what ends up happening when I have probability of 0.5 is, notice if I split this distribution where the mean is at 2.5, it's perfectly symmetric. The left and right side would like fold on top of each other perfectly. That's not the case with either of these. So anytime the probability is 0.5, we end up with a symmetric binomial distribution. In fact, if I increase n to 50, so here, 50 times 0.5, the mean would be 25. So the most likely outcome, the highest probability of occurring is 25. And then as I move in either direction to different numbers of successes higher or lower than 25, those probabilities are declining. Right? So the only difference there is it's still symmetric, but with n is 50, I get a little bit more of a, not as segmented of a distribution. It looks a little bit more smooth here, right? Okay. Any questions over any of that, or kind of, I don't know, just like, not like misunderstanding, but even just curiosity? Okay. Okay. So this one was just another one where n was a little bit higher, 20, the probability of success is 0.2. So the mean was 4. 4 is the most likely outcome. As I move in either direction, the probabilities decline. So you'll notice, to relate this to stuff that we've already talked about in this class, or this course, not today, not this class, but this course. When the probability of success is low, we get these long right tails, right? So a low probability of success, our binomial distribution is right skewed. High probability of success, we ended up with a long left tail or a left skew distribution. And then when the probability of success is 0.5, we actually end up with a symmetric or a normal distribution, right? So the shape of the binomial distribution depends on that probability of success, okay? So we'll keep moving here. I don't know why I still have this. We might talk about this today, we might not. Sometimes I think this just confuses people. Trying to relate the binomial to just a general discrete random variable. So we'll skip this for right now. And we'll kind of go through these. So if we were trying to look at these possible situations where I could use the binomial distribution, which of them is not an appropriate situation? Okay. So let's say I want to calculate the expected number or the mean coin flips that will come up heads out of 123 coin flips. Well, remember, the things we need for a binomial, we need a success and a failure. So seeing a heads or not, or seeing a heads or tails. The probability of success has to be the same on every experiment or every trial. So every coin flip, same probability of success of 0.5. They need to be independent from each other, which coin flips are. And I need to have kind of a cap, right? I need to know, like, I'm looking for the probability of seeing a certain number of successes out of a certain number of trials. So A is pretty good, right? If I had 123 coin flips, probably success is 0.5, I could find the mean by 123 times 0.5. So that's a perfect situation where I can use the binomial distribution. What about calculating the probability that at least 5 out of 20 patients get sick from an antibiotic? Right? Well, there I'm looking not just for the probability exactly 5, I'm looking at least 5, so 5 or greater, which is a little bit more work, but it's still different numbers of successes out of 20 trials. There's some underlying probability that, whoever makes this antibiotic, they probably even report, 5% of people get nauseous from taking this. So I've got a perfect situation. I've got the probability of success on any one trial. I'm looking for a certain number of successes, a probability of 5 or more, and then I've got my number of trials at 20. So this is a perfect situation we could use. In fact, to relate this to things probably recently, like I've looked at, some of the COVID vaccines, they put out the probability of certain side effects, and you could actually start to calculate, well, what's the probability, if 100 people took it, what's the probability that 10 of them get sick, or what's the probability that 2 of them, feel this side effect. And that's maybe not that interesting unless one of the side effects, which it's not from the vaccine, but from a certain medicine would be death. Well, then if I'm a company, I'm like, well, I got to figure out what the probability that, one person is going to die from this or something like that. So that's another perfect situation. What about calculating the probability an air traffic controller at the Muncie airport makes 3 errors per week? Well, I can either make an error or I don't, so it's kind of binary there. What's my number of trials? Is it the number of landings each week at the Muncie airport? Well, that changes week to week. Like what am I capped at here? All I'm given is a time period. Well, I don't have a number of trials, so I actually can't apply the binomial here. We'll actually talk about this on Friday, which is anytime I have like a time period and I'm looking for a certain number of successes over that time period, we're actually going to use a different type of discrete random variable distribution. So that's not going to work for us. So we know that's the answer. But the last one, you can kind of think about another example. If I had, what's the probability out of 5 customers, exactly 3 make a purchase once they enter my store? Well, based off of previous data, I could figure out once someone steps foot in my store, what's the probability they buy something? So I've got that probability of success for any one person. I want the probability that 3 out of 5, so I'm capped that number of trials that most I could see, 5 out of the 5. So this is another perfect situation where we could apply the binomial distribution, okay? And hopefully, once we talk about the Poisson, it'll make a little bit more sense why C doesn't work for binomial, and that the Poisson is actually a little bit more appropriate to use there, okay? Any questions at this point? I'm probably going to jump into Excel here for a little bit, okay? So I've got kind of the Excel slides here. I'll walk you through this here in a second. So we're going to use this example where I was looking at something in the last year that they had like good data for. In 2018, 6.7% of the U.S. population, and I put the population here, not in the world, but the U.S. population was considered millionaires, right? If you look at their assets and everything, they were considered millionaires. Right? So we could start to think of what's the probability that a certain number of people have, right? Exactly 5 people are millionaires. At most, or more than 8 people are millionaires. We'll work through some different examples, right? So this is what the slides will hopefully, match up to what we're about to do. So open Excel here. Make sure that we can, there we go. Make sure we can see everything. Okay. So let's say I want the probability that exactly 5 people out of 100 random people that I ask are millionaires, okay? So what I can do is use this binom.dist function. Right? I could say, well, what's the number of successes? Well, I'm interested in 5, right? What's the number of, and then comma. The second thing it wants is what's the number of trials? 100 random people. What's the probability of success in one trial? Well, if 6.7% of people in the U.S. are millionaires, if I grab someone at random, the probability any one person is a millionaire is 0.067. And then this last thing, comma, we're going to have to tell it, do we want this to be cumulative? Well, we're looking for the probability of exactly 5, so no, we don't, or false. Or the way I always kind of do this is I just use ones and zeros. 1 is true, 0 Excel recognizes as false. Okay, just a little bit quicker to type. So if I hit enter here, what Excel is going to do, instead of me plugging in 5 as x, n is 100, and p is 0.067, and then doing all the math, using those factorials, typing it in my calculator, Excel is going to do all that work for me. Okay, so I hit enter, and I get the probability exact 5 out of 100. It's about 14%, or probability of 0.14. Okay, so that's not too bad. If we're thinking about what is the general form of the equation, well, it's typically, we're going to think about this as the number of successes, comma, the number of trials, comma, probability of success. And if we don't want it to be cumulative, right, we put a 0 in there. We're looking for the probability of exactly a certain number of successes, or one number of successes. So that's the general form of the equation. Right? And you can use this, it's probably good to also know how to kind of do it by hand in case you run into one of those scenarios where n is really large and you want to kind of cancel some things and make the math easier. But you could use Excel to kind of help you as you're working through that Connect assignment. There's a couple questions on the Excel assignment that are binomial at the very end. So one thing you could do is set this up so that we've got these 3 different things. So the x we were interested in, the number of successes was 5, n was 100, and the probability of success was 0.067, right? So go back here to our general form of this equation. The first thing we tell it is, so I'll delete that, the number of successes we're interested in. The second thing is the number of trials. And the third thing would be that probability of success. Okay. Now notice, this one, everything is kind of locked into those values. But let's say I've got a couple questions in a row. So it's like, what's the probability x is equal to 10? Well, now all I do is I change the 10, and this spits back out at me the probability x is equal to 10. Okay, well now it's 2021. I got some new data. Actually now 0.071%, or sorry, 7.1%, or a probability of 0.071 of people are millionaires. So I can type, it just keeps updating things for me using those cell references. It's a little bit easier to kind of see what you're putting into that formula, okay? But if we change this back, I'll show you something else that's will be kind of a nice little trick, right? So the lowest I could see is 0 out of 100 people be millionaires, then 1 people out of 100, so on and so forth. So a nice little trick in Excel, if I right-click and drag this down and hit Fill Series, it'll just keep going up by 1, okay? So I'm going to type in here that binomial distribution. So the number of successes I actually have over here on the left side now, comma, number of trials, comma, probability of success. I don't want it to be cumulative, right? I want to find the probability it's equal to 0, probability it's equal to 1, probability it's equal to 2, so on and so forth. So as I copy this down, I want the number of successes cell reference to keep updating, but I don't want the number of trials or the underlying probability of success to. So what I'll do is I'll highlight these, Command T on a Mac, F4 or FN F4 on a non-Mac, and I freeze those. So now when I copy this down, and there the trick was, remember, if I double left click here, it'll copy it all the way down. Excuse me, it'll find the probability of these different numbers of successes. Okay. So we're going to use these so I can kind of sell you on the next thing this binomial distribution function will do. So let's say I want the probability, and I think I have at most 8 on the slide. So we'll do x is less than or equal to 8. Right. So if I want the probability x is less than or equal to 8, right? Well, what I could do is I know that's just the probability x is equal to 0 plus the probability x is equal to 1 plus the probability x is equal to 2 all the way up to the probability x is equal to 8, right? So I could just add up this work I had over here, right? Add up the probabilities from 0 all the way down to 8. Okay? We'll hit enter. Right? And that would be that cumulative probability. But the nice thing is Excel has built into this binomial distribution function, or binom.dist, if I want the number of successes to kind of stop at 8, right? comma, number of trials, comma, probability of success. But now I want it to be cumulative, right? What I want Excel to do is find the probability that X is equal to 8 and add to that every single probability below it, right? Or essentially give me the probability that X is equal to 8 or lower, right? Or make it cumulative, right? So all I do there is change the very last thing that I had as a 0 to a 1, and that makes it cumulative, okay? So now when I hit enter, notice I'll get the exact same thing, but I didn't have to do all of this work and then add up, the outcomes that fit that, okay? So it's two ways of doing the same thing. Using that cumulative option, makes problems like this. All I had to do this was in one cell, right? Made it a little bit easier, okay? Any questions over anything up to this point? Where are we at in time? Okay, we're fine. No questions? Sure? All right. So here's where things get maybe could be a little bit trickier. What if I wanted the probability that X is greater than 8? Or, yeah, I'll do greater than 8. All right. Well, if my number of trials is 100, that would be the probability X is equal to 9 plus the probability X is equal to 10 plus all the way up to 100, right? Well, I could fill this out and then do the sum function, but that seems like a lot of work. If I think about this as event A, what would the complement of A be? So if X is greater than 8, the complement of that would be that X is, less than or equal to, right? I have to remember that 8 has to be in one of these, right? So less than or equal to. So if I find that, well, I already found that up here. So in order to find the probability X is greater than 8, I could just do 1 minus that. Or if I hadn't had this previous work done, 1 minus binomial.dist of 8, comma, the number of trials, comma, probability of success, comma, I would have to make it cumulative, right? That's what I was doing up here. I was saying, take the probability that X is equal to 8 or anything below it, that would be our complement. So now if I subtract the complement from 1, that should give me the probability of the event that I want. Okay? So kind of what we were doing in hand with some of those problems earlier, but using that binomial.dist instead of finding all this by hand, which would be a pain, right? If I did this by hand, I'd have to find the probability X is equal to 8 using the equation, then add to it the probability X is equal to 7 using the equation, and kind of keep on doing this. So I have to use the equation 9 different times. So Excel could save me a lot of time here. Okay? And sure enough, we think about this, well, if this was event A, and we said here is our complement, these two things should add up to 1. Sure enough, you kind of can see that they will. Okay? Any questions on that before we keep moving? You want to see one of these cells again, or just a general question? All right. So I'll show you one that's a little bit harder that can kind of trip us up. Okay. Let's say I want the probability X is greater than, or equal to, I don't know. Let's choose some other number we haven't used yet. So let's do 6. All right. Well, what I don't want to do is say, okay, well, I'll just do 1 minus the complement, right? I mean, that is what I want to do. When I'm finding the complement, if I put in 6, comma, number of trials, comma, probability of success, make it cumulative, and I'm thinking, oh yeah, I'm just taking 1 minus the complement, that'll give me the probability of the event. That's great. Well, what's a problem with this? Yeah, so we got to be careful when we have that equality here, because if this is A, the complement would actually be that X is less than 6, which here, remember the equation, whatever number you tell it, it includes that probability. So it's treating this as though I'm saying, what's the probability X is less than or equal to 6? What I actually just want is, what's the probability X is less than 6? Well, the very first outcome that meets that criteria would actually only be 5, right? So that one gets, a little tricky, because the way we have to write this in Excel, if I'm doing it by hand, it's easy. I can just write less than 6. But in Excel, this function, there's no option to just put less than. It always treats it as though it's less than or equal to, right? It always treats it as that. So instead of being, so if I want less than 6, what I actually need to tell it is less than or equal to 5, right? So I need to use the 5 here. So that's a little bit tricky if I had a scenario like that, okay? When I just had just the greater than sign, it was I used that value because that value is actually in the complement. So it's a little bit tricky there, but we could kind of find that as well. Okay? And you can imagine I could actually copy this all the way down, and I could play around with doing this all manually, like adding up, right, using that sum function. Now notice, if there's 6.7% of people are millionaires, on average, how many people out of 100 would be millionaires? We said that was just n times p. So 100 times 0.067 would be 6.7 people on average out of 100. So the probabilities, the most likely outcomes I'm going to be seeing are 6 and 7. Sure enough, if I look at these, 6 and 7 have the highest probabilities of occurring. And as I move away from that mean of 6.7, notice what happens to my probabilities. If I move in this direction, they start to decrease. And if I move in this direction, they start to decrease. But if you think about it, if only 6.7% of people are millionaires, by the time I get to well, what's the probability I see 20 out of 100 be millionaires? Well, if on average it's 6.7, and you're really asking what's the probability 20% of these 100 people are millionaires, it's going to be pretty low. In fact, e to the negative 6, remember, means move that decimal point 6 places to the left. So this is 0.00069, pretty close to 0. As I keep going higher and higher, by the time I get to what's the probability that, let's do, I missed it by 1. What's the probability all 100 people are millionaires? I mean, this is astronomically small, right? It's just so close to 0, we might as well say the probability is 0 at that point, right? So this is kind of doing this by hand, kind of is a, gives us a nice little visual. Where you at in time? I want to end this at the same time as the others. Do you have a question?
On the, so it's 6.7, but the 6 is higher than 7 here. Why is that?
So how can I think of a best way to explain this? So when the mean is in between two values, remember the mean is influenced by large values. Even if, and this is like a weighted mean, because we're using the probabilities as our weights, but think about it here. We've got all these outcomes, which yes, the probabilities are low, but they will influence that mean, right? So all of these values that are really extreme outliers, yeah, the probability is low, but they still get factored, they still do pull that mean up a little bit. So even though the mean is closer to 7, it's not that 7 is more likely to see than 6. That mean is being influenced by these unlikely outcomes, right? So even though the values down here, like 15 and 14, right? Those are kind of pulling that mean up away from 6, even though 6 really is the most likely outcome, right? The mean is actually, so it is kind of tough to think about when we're looking at an example like this, because with a lower probability, we're going to have a lot more possible numbers of successes on the right-hand side, right? If I look at the mean here is 6.7. Well, there's only 6 outcomes to the left of that. There's more than 90 to the right. So because we have a longer right tail that pulls the mean to the right, and it kind of has this counterintuitive thing where oh, the mean 6.7, 7 should be more likely than 6. Well, no, not necessarily, right? Because that mean is being influenced by those outliers. That's a really good question, actually. But you can kind of see, those are the two most likely outcomes, even though 6 is a little bit more likely than 7. Any other questions? That was good. I like that, actually. I actually didn't even see that there. So it doesn't. Oh, and this is kind of an extreme example. So this is the fact that it happened here. You probably don't see it happen a lot. Quite often, your thinking originally would have probably been correct, right? That 6 or 7 would have been a little bit more likely than 6 usually. Let's actually, I don't know if this will do what I want, but we'll try. So if I select these, yeah, there it goes. Nope, that's not what I wanted. So if I select all these probabilities, and then I just put them into a column chart, and then I'm going to go down here, select data, select those numbers as the possible outcomes. Okay. You can kind of see like the outcomes from 0 to about 16 are the only ones that really have any real probability associated with them. The other ones are so close to 0 that visually they don't even show up, right? So this is actually kind of one scenario where this graph is nice. It kind of gives us an idea about the distribution, but it almost looks like these don't exist, and it's just because those probabilities are so low, right? But you could, like with some of the other examples we've done, you could also kind of create those visual depictions of the binomial distribution for whatever example you're working on as well. Okay? And the only trick was there, I had to select the probabilities and then go back in, select data, and change the axis labels to be kind of these different outcomes. Otherwise, I think it starts it at 1, right? And we know that it actually should start at 0 because 0 is the lowest possible number of successes we could see. Okay? Let me save this real quick. I'm going to put this on Canvas after class. So, section 5, binomial. Oh, we'll just save it there. I'll remember it's there. Are there any other questions on anything in Excel? I can pull it open again. We can look at it, or just any questions about the binomial in general. Okay. So knowing that complement rule really helped us today. Remembering kind of those tricks like 0 factorial is 1, anything to 0 power is 1. Those are some important things that you might not kind of pick up from the slides, or if you're kind of going through this video quickly, if you're watching after the fact. Those connecting Excel assignments due the end of the day next Friday. So start working on those early, because next week we'll pretty much just be doing exam review. We'll probably be working through a few more Poisson distribution examples, which is what we'll talk about Friday on Monday. But mostly next week is going to be review. And then I'll talk a little bit more about when the exam is going to be available next week, or early on in the week, so like on Monday. But tentatively, I'm kind of thinking about, I said usually I'll make it available Thursday and Friday. I'll probably give a longer time window that kind of covers even through it kind of crosses over the weekend, just to give you some more, freedom with your schedule. But also we can get one more kind of review session in there Friday, so you can get a look at some practice problems, have questions to ask me. Okay? Any other questions for me before we get out of here today? One in the chat. All right, I'll leave the Zoom open a little bit if there are any questions as people are kind of heading out. Other than that, see you guys on Friday.